Friday's class by giving you four substances and asking you to pick out what type of substance it was and what the IMF was. And as you looked at that, we were trying to also figure out how you made your decision. If you look at these four, you can see, I guess the quickest thing to see is that there's only one with a metal in it. Lithium is a metal. And so if we identify a compound that has both a metal and a non-metal, then we can look at this and say it is ionic, right? It's an ionic compound. And we are looking for the presence of a metal and a non-metal. Right, and so there's that. And the IMF for that is an ionic bond, right? Or if you want, ion-ion attractions, right? So you can say ion-ion attractions if you so desire. So this is everything there. And then we're looking for other things. Well, if we look for polar covalent, we can see that we have a polar covalent compound here. And we see we have a polar covalent compound here. Actually figure out whether H2S is polar or non-polar or what, we have to actually draw it. And so we can draw it like this. We can draw an H. And we can bond it to an S. Maybe another H. And we can draw some dots. And we can decide that this thing is AX2E2. Okay. And if it's AX2E2, we know that it is bent, right? And so it is asymmetric. Okay, so this guy is bent. Okay. And so we know that it is going to be polar. So you're looking for something like this, you're looking for asymmetry, right? Or you're looking for unequal bonds, right? It doesn't have to be both, but it does have to be one of them. And you're looking for that. Now the question is, what about this guy? This is polar covalent. But if you look at NH3, what it is, it looks like this. It has H, right? Oops. So it has an H. It has an N. It has another H. Right. And it has a pair of dots. So this guy has one of these special polar covalent compounds that has either NH or OH, right, or FH, right? And we're looking for one of these three, and we're looking for, they need to make sure we have dots on them, right? We need definitely have to unshared pairs. So this thing here is not just polar covalent, it is polar covalent with hydrogen bonds, right? So that's important, that we're looking for one of the special polar covalent compounds, so it has hydrogen bonding. And so the IMF for this one is hydrogen bonding, right? And then for this guy is just dipole-dipole attraction, right? Dipole-dipole, dipole-dipole. All right, so dipole-dipole attraction, which just means we have the weak plus-minus attraction. And then CH4 is left behind. CH4, if we draw the structure, notice that we're drawing structures for all these molecular compounds, right? CH4 is a C, and it has bonds going in four directions, so it's an AX4. And they are all H's, so they are equal bonds, and they are symmetric because it's an AX4, right? And if it's equal bonds and it's symmetric, it should be a non-polar compound. And so this is our Lewis structure, and so it is, we're looking for equal bonds, and it's symmetric. It's an AX4, and so that is non-polar covalent. So there are four types of compounds. Oh, the IMF for this, of course, is London dispersion forces. So here are forces, and here are look-fors, and our types of substances. But when we did this, we then said, okay, let's look at what the boiling points and melting points are, or the boiling points are. And what we did was we just used Dr. Google, and we looked up the boiling points. And if you look at this, whoa, right, the boiling points, the highest boiling point here is for the ionic compound because it has the strongest interparticle forces. The next highest, right, which is not very high at all, is actually at -33, and that's our hydrogen bonding. So this is clearly the strongest. If we look at this, we can say that this guy is the strongest, right, by far. And let's put this up here. Right, so this is our strongest. Where can we put it? Oh, let's put it here. Strongest, right? And then this guy is kind of weak, right? This guy is weaker. Right? And this is weakest. Oh, stop that, you dummy. I did not ask you to type on that. Right? So this is our weakest. And so you can see that if we predict that LDF is our weakest bond, a weakest interparticle force, that makes sense because it is at -162, which is only about 110 Kelvin, right? It's relatively close to absolute zero. Our weaker one, our polar covalent one, is down at -60, right, which is pretty chilly. So H2S stays a gas until -60 degrees Celsius. Ammonia, which is the stuff you have on your sink, NH3, it has a weak attraction, and it vaporizes at -33, so not a lot higher than H2S. And then LIF, which is ionic, doesn't boil until well over 1,000 degrees Celsius. So you can see that is the strongest. After going over this, we talked about solubility. And the rule we went over was like dissolves like, which essentially just means that polar substances dissolve in polar solvents, nonpolar substances dissolve in nonpolar solvents. But the question is why, right? Why does that work? And you need to realize that when something dissolves, three things have to happen, okay? So dissolving involves three processes, or three steps, or three parts. Let's just call it three parts, right? The first thing is, right, the solute and solvent. I guess the first and second. The solvent has to break apart, right, into individual molecules or ions. Similarly, the solvent has to break apart also. And the solute and solvent have to mix. Right? They have to mix, or I guess attract each other. Now the thing is that if we look at this, this absorbs energy. Right? Breaking apart molecules absorbs energy. Well, that means that this absorbs energy. Well, things that absorb energy don't happen very easily, right? You have to add energy to get them to happen. They don't happen on their own. However, the attraction then releases energy. Right? And so for something to happen, the attraction has to be fairly strong because it has to be at least as much release of energy as it takes to break the solute and solvent apart. But here's another way of looking at it. Basically, if the attractions are similar, if they're similar in strength, to the attractions within the solute, then mixing occurs because there is no, energy gain, right? Or there's no right? As far as the solute and solvent are concerned, if the attractions are the same, then we know that it's releasing about the same amount of energy as it's gaining, and it just sort of randomizes, right? And the way I picture this is by thinking about going to a party or something. If you want to break, like if you're in a group, like if we go as a class to another school, you have some attraction to your classmates. If you want to break apart and join the other members of the school, you have to be at least as attracted to that group as you are to your own friends, right, in our class. And so you'll break apart if you feel fairly comfortable with them. So if we went to a Wheaton assembly, you'd break apart and you just sort of mix into the assembly. You'd sit with whoever you sat with. But if we went to another school where you don't know people, the attractions within your group are stronger than the attractions to that other student body, and you would probably stay as a class. You may not be horribly attracted to the people in your class, but probably more than you are to strangers, right? And so you'd stay together. And the same thing happens here. If we have nonpolar substances and we try to dissolve them in water, the attraction between the water particles is much stronger than the attraction between water and nonpolar substances. And so what happens is the water simply stays together and doesn't break apart to accept it in. Similarly, if we have a really large ionic compound or a really large polar compound, the attractions between the polar molecules may be large enough that it won't break apart to go into the water. But if the attractions are similar, then it breaks apart without difficulty because it doesn't really notice that it has changed environments, right? Anyway, so this is the way we think of it, that like dissolves like. But what that means is if we, right, one way of looking at this is that if you have a nonpolar compound, right, it will dissolve best in oils, right, or petroleum solvents, right, like kerosene, right, or benzene or whatever it is, right, petroleum solvents like kerosene or turpentine, right. So when you go to Home Depot, you see this whole rack of non-water-based solvents that are meant for dissolving things like oil-based paints, right, because they don't dissolve well in water, right. If you have a polar or ionic compound, if you have a polar or ionic compound, they dissolve best in polar solvents. And by polar solvents, we usually mean water, right? So usually when we're talking about polar solvents, we're just talking about solvents like water. But there are other polar solvents. Methanol is fairly polar, right? It's not as polar as water is, but it can dissolve many polar solvents, solutes. And acetic acid is polar as well, and it can be used as a solvent in some situations. So water isn't the only polar solvent, but since it's pretty cheap and it comes out of a tap, we're going to say that mostly when we're talking about polar solvents, we're talking about water. Now, we did an activity, and I will open a recording of that activity, and let's see if I can find that. Maybe this is it. No, that's not it. What did I do with? It's called chromatography. Let me just open file. See if I can find it. Chromatography 2. And so I will turn the sound off on this so I can talk about it. But this is what we did in class, but I did it on my tabletop so we could see it clearly. Okay. So all we did was evidently adjust the camera for friggin' ever. And no, we took two pieces of filter paper and we dotted them with two kinds of markers. Okay, so on the left side, I have permanent markers or Sharpies, and I use two different colors. And I'm doing the same pattern on both papers. So I have a brown Sharpie and a green Sharpie. So we made two permanent marker dots on these pieces of paper. And this is awfully exciting. But then what we did was we took water-based markers, or washable markers, and of the same color. So I have a brown here and a green coming up, and we made a brown and a green dot of that. And then we just took two beakers with two different solvents in them. And let's see if we can change the playback speed. Maybe we can. Go 1.5 speed so we don't have to watch quite all of this. So I'm not the fastest writer in the world. So we have water. That works pretty well. Let's do it twice. There we go. And if we look at the Lewis structures, you can see the water is polar with hydrogen bonds. It has OH with two unshared pairs of electrons. And isopropyl alcohol also does hydrogen bonding, right? And so you'd say, well, these aren't very different. But what's really different about it is that isopropyl alcohol has these 3 carbons on the left, and we know that carbon-hydrogen bonds are very nonpolar, so it has this large nonpolar chunk off to the left. And that means that overall, the molecule is a lot less polar than water is. Okay. Now, it's not a nonpolar solvent, but it's a lot less polar. Okay. And so we're going to use water as a polar solvent and isopropyl alcohol as a less polar solvent. Okay. And we'll put both filter papers into the beakers and clip them there so we can look at them. And you will see, amazingly and astoundingly, the solvent will wick up the paper, and if the ink dots are attracted to the solvent, they will move with the solvent. And you can already see on the right that the washable marker moves with the water quite quickly. So the water is moving up the paper very quickly. And that actually, by the way, is another polarity effect. Paper itself, cellulose, has lots of OHs in it. So cellulose has lots of polar sites, and water actually spreads out onto paper much more effectively than a non-polar solvent like isopropanol does, right? Or a less polar solvent like isopropanol does. So isopropanol doesn't wick as effectively up the paper as water does, right? But you can see pretty quickly we get this wicking up the paper. And if you look at it, you can see separation of the dyes in the water side, because even though they're all attracted to water primarily, right? Oops. Let's go back for a second and pause. Right? Even though they're attracted to water primarily, right? Different dyes have slightly different attractions, right? So the green dye is less attracted than the blue dye within that green marker, right? So you have this greenish dye here and a blue dye above it, and the blue dye basically is incredibly water soluble, and the green dye a little bit less so. Similarly, in the brown marker, you see we have at least 2 dyes. We have the pinkish dye at the bottom that is mostly attracted to it, but then we have this blackish greenish dye above it that moves much faster. What's interesting though is look at the dots. The dots for the water-based marker have almost completely disappeared. So almost none of the water-based ink is left at the bottom, right? Whereas the permanent markers basically didn't move. They weren't soluble in water at all. And so when water passed by, they simply stayed bonded to the paper or attracted to the paper, right? So let's look at the other dots then, and let's see what they look like. Now the isopropanol moves a lot slower on the paper, but you can see it's moving up the paper some. What I think is readily apparent is that the permanent marker dots are clearly moving, whereas the water-based markers, some of the ink is moving, but you can still clearly see the circular dots at the bottom. So the ink as a whole is staying put, but that's not to say it is completely insoluble, just that it's much less soluble, right? Now on the left, you can see that the dots are pretty much completely gone from the bottom. And so the permanent marker is relatively attracted to the isopropanol. Okay. And so we will fast forward a little bit. Not that it's not great to watch it. Let's scroll ahead and see if we can get the paper out of there. There we go. And so that's what it looked like at the end. And if we pause and behold the majesty of this, whoa, right? You can see pretty clearly we have the water-based markers which move with water because like dissolves like, right? The non-water-based markers stayed behind. But when we used isopropanol, the non-water-based markers moved pretty well, and the water-based markers did not move much at all, right? Okay. And so you can see that chromatography works by differences in solubility, right? The more soluble something is in the liquid phase, the more it moves in chromatography. The less soluble something is in the liquid phase, the less it moves in chromatography, right? And if we change the solvents, we change what stuff moves. Anyway, that was the whole of that, and hopefully that was helpful.